Go.
All right. Good afternoon, everybody. My name is Michael Robler. We're going to talk about implementing Celery. And let's get started. So basically what we're going to talk about today is implementing Celery. We're going to do a super quick review. There was an excellent talk yesterday on Celery. So hopefully if you don't know what Celery is, you went to that talk. I'll give like a few basic bullet points on it, but watch that talk if you need a lot more details on the basics of Celery. We're also going to talk about what we did at OnShift, the company I work for, before we were using Celery, which will kind of give you a reason why you should use Celery for these type of problems. We're also going to talk about how to handle various problems that you're going to run into when you actually try to implement Celery in a real system. Things like I have multiple environments, I need to handle priorities, I need to handle failures, I need to work with my ORM, and I want to work with the database directly in some cases too. Hopefully we'll get to that one. It's kind of a bonus feature if we get to it. All right, so who am I? I'm the senior architect at OnShift Incorporated. We make scheduling software for healthcare. I'm also the director of technology at EHR Tutor, which is a startup that is making software to help students learn the basic concepts of electronic health records. We're also playing with some really cool polling software, which you guys may have seen in the lightning talks last night. We're trying to get bugs worked out of that. I wrote a computer game called Railroad Empire a while back. It's no longer active. And last year I gave a talk about ORMs here at PyOhio. So I have talked here before. So what did we do before we switched to Celery? So we have an issue in our application where we want to do real-time data gathering and put it into a data warehouse. And in order to do that, originally what we did is we basically implemented a queue inside of Postgres. And every time we made a change to a table in the database, we basically stuck an element in that queue that said, hey, you need to go and move this over to the data warehouse. And we ended up having the worker process, kept reading that queue, and read it. Kind of worked. I mean, it worked okay, but we were getting up into the point where we were doing millions of these. A day, and that began to really cause some problems with Postgres. Postgres has a lot of really good concurrency things. It has row-level locking and all this stuff. But when you start doing millions of things and you're doing, 100 or 1,000 things in a second, you get to these edge cases that concurrency still causes problems, even with things like row-level locking and stuff like that, where everything would be fine except one in a million things would be duplicated. And that's not something you want when you're doing queues. You want each thing to be executed once. You don't want something to get executed 2 times. We came up with some workarounds for it, so you can still do this in Postgres. But in order to do that, we basically had to shard the table based on some factor so that one worker could only ever access one section of the data, which doesn't scale real well. It has some scaling issues. Other things that we saw table bloating issues. So we're putting millions of things in there in a day. This table would go from being, having 1,000 items to it to having hundreds of thousands back to 1,000. And the size, according to Postgres, the size of this table was huge when in reality it was small. Vacuuming became a problem for it. So, it just ends up that when you get to really big things, for small things, a queue in Postgres works okay. But when you start to get to doing big things, Postgres is not a queuing mechanism, and it doesn't work well for that. So we were looking for a better alternative. And we decided to choose Celery and RabbitMQ. So I just realized I skipped an entire slide, or it's not on here. Aha, I just skipped it. Sorry about that, guys. Okay, so we chose Celery. That's actually will work, though. So we chose to use Celery. So what is Celery? Celery is a library for doing queuing in Python. It doesn't actually implement the queue itself. It is just a library for using a back-end queue. Most of the time, people use RabbitMQ as their queuing library when they're using Celery. You can also use Redis. I believe you can actually use Postgres as a backend is one of the options. There's several other backends, but Celery was really built to work with RabbitMQ. It has a lot of specific stuff to make it work well with RabbitMQ. And it uses the AMQP protocol to talk to RabbitMQ. So theoretically, anything else that uses the AMQP protocol can also work with Celery. And one of the other things that's important to know is your workers in Celery. So, when you're doing a queue, you have workers are also called consumers. In Celery, by default, those are it's multi-processing. So you have one worker, one process. You can do multi-threaded queues and things like that, but that's not the default. And generally, it's Python. You got the global interpreter lock. Stick to multi-process. Is that. So at OnShift, when we decided to use Celery, we decided that we were going to use RabbitMQ. So my talk is assuming that you're using RabbitMQ with Celery here. Also, Celery has a bunch of features that we are not currently using, so I'm not going to be talking about results. Celery has an ability to send back results whenever you are working with a queue. What I'm assuming here is these are offline tasks where you've gone and you've done something on your web application or whatever application, and you want some other backend process to do some additional work afterwards, and you don't care the fact that it's done, it just needs to get done. You don't care that it got done. The other thing is Celery has some really cool advanced routing features and workflow features where you can do things like chords and maps and stars. I'm not talking about that. I believe that there is actually a talk later this afternoon about that very topic. So if you are interested in that, I would go to that talk. I can't remember the name of it. So. Okay, so now we're going to talk a little bit about the actual things that you are going to run into if you start using Celery in a big environment. So at OnShift where I work, as an example, we have 5 different stage testing environments that our QA people use that are all on one box. So there's basically 5 different copies of the code there. We did not want to run 5 instances of RabbitMQ and have to figure out ports that they're talking to and stuff like that. It didn't make sense for what we were doing. So instead what we chose to do is we used we basically said every single queue is going to have a name attached to it that is defined, so we could have stage 1 dash whatever the queue name is, stage 2 dash whatever the queue is. And then what we ended up doing is having our configuration system tell each thing what to write. So what we ended up doing, our stuff is in TurboGears. Yes, it's that old. It's actually TurboGears 1.0. So what we basically did is we wrote a function that gets the queue, goes to our configuration system in TurboGears, looks up the name that you pass it in, and then gets the actual name for it for the queue. So when you're going and defining a task, which is the second part of this, this area here, when you're defining your task, when you define what queue you want, rather than just saying, I want the high queue or the medium queue or the low queue, which we're going to talk about that a little bit more, you say, I want to get the name for that queue for my specific implementation for the high or the medium or the low. It's a fairly, it's a fairly brute force way to solve the problem, but it works. So you saw that one of our queue names was high. So priorities. What we ran into was a problem of we had queues that we were using for a number of different things. We had queues where we had really high priority things that were the user clicked on something, and we wanted to make sure that that data got fed into the data warehouse right away. So if they ran a report on that data that they just put in, it would be in there as quickly as possible. Then we have stuff where we send messages where they say, hey, I need a person to fill this position, send a text message to that person. And then we have these really long-running, low-priority things where we have integration systems that are pulling this data in from third-party vendors and stuff and putting it into our database. And then, obviously, we take from the database to the data warehouse. And those things take a long time to run. Well, what was happening is those things that take a long time to run, if we had 8 workers running and we happen to get 8 of those at the same time that take 5 minutes to run, all 8 of our workers are now being used by the low ones, and none of our high stuff, none of our higher medium priority stuff was getting done. So to solve that problem, basically what we did is we grouped our stuff. We chose 3 things to group into a high, medium, and low, and that's how we ended up solving that problem. So now the high priority, really fast stuff has one queue that serves its stuff. Medium stuff has its own queue that serves it, and the low one, we don't care how long it takes, so it can go and take all the time it needs. And if the stuff backs up, as long as we have enough workers in order to make sure it gets done during the day, we don't really care. And then the other thing that's nice about this is you can dynamically, in Celery, you can dynamically add workers to queues as it's running. So if for some reason we do see one of them is backing up, all we have to do is bring up another machine and have it start processing the workload by the other worker for a particular queue. And then we can go and drain a queue a little bit faster if it starts to back up. And we have done that. When we want to rebuild sets of data, sometimes we put large amounts of stuff in the queue, and we use the queue to rebuild data sets when we need to, which is kind of a nice bonus feature that we get out of using the Celery and the queuing. Now, this is probably the biggest issue that we ran into when we started to implement Celery. Celery is, the documentation is great for telling you how to do things when they work. But when things start to stop working in your code, Celery doesn't really give you a whole lot of insight into what you should do. You can retry, they tell you about that, but that's about really the only thing that they tell you about. Well, it's not always appropriate to retry your thing. If the reason that your failure is occurring is because there's a bug in your code, you could retry it all day long. It's going to keep failing until you fix the bug in your code. So that's really not the right thing to do, because all you're going to do is waste cycles on your queue. And if you have a lot of stuff going on in your queue, you don't want to be wasting cycles. So to solve that, we decided to create a failure queue. And when something fails in a way that it is not acceptable to retry it, we put it in the failure queue. And then we also wanted to make sure that when something was failing, we knew that it was failing and wasn't just silently disappearing into the ether. So when should you retry something? If you are trying the task again with no other changes and now it's going to start working, then it's a smart idea to retry it. So for instance, if the reason that you got your failure was because your database had a deadlock in it, or the server was busy, or the server was temporarily unavailable, or some other thing that should resolve itself without you doing anything else the next time you try to run it, or if you try to run it again in 10 seconds or 15 seconds, then it's appropriate to retry it. Of course, the corollary to that is if every time you retry it, it's going to keep failing, then don't bother trying to retry it. Unhandled exceptions from your code obviously would fall into this. Permanent email address failures, if you're trying to send an email and you get a message saying, hey, this email address doesn't exist, well, clearly there's no point in trying to retry it. In our case, it's actually text messages and it says, hey, this phone number doesn't exist, or something along those lines. So what do you do with those ones that you can't retry? What we decided to do was we put them into another queue. This is our failure queue. So when your task has failed and retrying it is not useful, then that's when we stick it in our failure queue. And then the nice thing about putting it in a failure queue is once you've fixed the problem and you've fixed your code, push it to production, and you're ready to continue to have things work, all you have to do is attach some workers to your failure queue, and they will go and consume all those things, and they will try to rerun them. And everything that was fixed will now just get consumed and get out of the queue, and then obviously if you still had other things that were still failing, they would fail again, and you would see that, so you would know if there were other things that were still failing. So we've used that several times to fix some problems in our code, and it's nice because that means you aren't losing it. If you have things that you need to make sure get sent or get done, they're not going to just disappear because it failed. You can rerun them and keep the data without losing the data. So the other thing is, okay, so I had this failure and I put the data in the failure queue, but how do I know that that data is there? How do I know that something failed in the failure queue? I mean, you could go to your monitoring software, which hopefully you've set up because this is production code and you are hopefully monitoring it with whatever your favorite monitoring tool is, and see that there's things in the failure queue, but that doesn't really help you if you're at home having a margarita on the deck or whatever you're doing. In which case you need something to tell you, hey, something bad went wrong. In our case, we actually use Celery, which is a pretty good service for that. It is not, by far, not the only thing out there to do this type of thing. But it happens to be what we use, and it works well for this. So here's an example of how you can do this. So in Celery, one of the things that you can do is you take, when you're creating a task, you can define the base task of what you want your Celery queue to be referring to. And when you can create your own based classes that are inheriting from the default Celery task. And when you do that, you get a whole bunch of hooks that you can override to do custom stuff. And onFailure is one of those hooks that you can define. And when you define your onFailure hook, what we end up doing in our case is we check to see, hey, do we happen to have Celery set up? And if we do, then we can go and actually capture that exception and put it in, we can actually capture that exception. And so that's kind of how we do that. There's another interesting thing in here. There is this, I know a lot of people probably say, oh, you're using isInstance. I actually happen to like using isInstance. I'm sure we could have a debate about that. But what we're doing here is we are basically saying, hey, if the exception that got thrown was caused because the user did something stupid, which all of our user did something stupid exceptions are inherent from user error in our system, then we don't want to bother to notify people because I really don't want to get a bunch of notifications while I'm at home drinking a margarita or whatever. I actually don't drink. That's why I think this is funny, and anybody that works with me would think that's funny. Anyways, but while I'm at home doing whatever it is I'm doing, I don't want to know every time, Joe Smith happened to type in the wrong telephone number for the person that they're trying to send a text message to. I don't care. That was their mistake, not mine. So we have those things throw user errors, and we don't bother to put those into exception. Now, one of the things that we have decided to do here, and whether or not this is a bug is actually up for debate, because I actually saw this, and a couple of us at work saw this when they were going over when I did this presentation at work to test it, is because of the way this is written, if you happen to have a user error, or if Raven happens not to be set up, it's not going to end up in the failure queue because this last line is what puts things in the failure queue. So this is actually probably a bug in my code that I need to really look at, because even if you don't have Raven configured, you probably want to put things in the failure queue, but you probably don't want to put them in there if it's a user error. So I actually need to fix that. But that is how you put things into the. That's how we put things into the failure queue. You just call apply async. So you can actually call apply async from inside your workers. If anybody didn't know that, you can use apply async inside of your workers to put things onto the queue from inside a worker, which is actually pretty useful to do. So now that we've got all that and we have everything working and production's going great, now all of a sudden we say, oh, we hate using turbo gears and SQL object, and we are going to rewrite our entire application and we're going to use SQL Alchemy. Oh, okay, I got more work to do now. So in order to do that, what we realized is we were going to need some integration with SQL Alchemy in order to make things a lot better for our new code. And one of the things that we wanted to do, which we have a problem with in our current implementation that we decided to fix when we were working on this rewrite, was we wanted to make it so that when we create a task, we don't want that task to immediately go into the queue. We want to wait until the database transaction is committed. That way, if the transaction rolls back for whatever reason, we aren't putting the thing in the queue. We also don't want to one of the other things that we do in our current implementation that can be a problem, for the same reason really, is because you don't know how fast your queue is going to consume your worker, you need to make sure that the database is up to date and been committed before you actually put the thing that is going to use it in the queue. So what we have to do is we actually do a commit and then put things into the queue in our current code. Well, if we have more work to do after that in our current code, if something fails in that current thing, you could have the potential thing where you have half of the work has been committed and half of it isn't committed. It's not the right way to do things. Luckily, we've been lucky so far, it hasn't caused us problems. But as a good software developer and as an architect and the person that's supposed to be making sure we do good things in our code or our business, I decided, hey, that is not the right way to do this. We need to fix this problem. So in our rewrite, we did decide to fix this problem. And this code sample's a little bit longer, so I stuck it in an IPython notebook. Can everybody read it in the back? Yep, okay, good. Okay, so what we ended up doing is we made a list. It's a global. I could have done this differently, but I was lazy. There's basically a global list that we have because this is multi-processing and we only have one process running, so it's fine that it's a global. You're not going to have any sort of contention issues here. So we have this list, and then what happens is whenever you want to call apply async, or if you're calling delay actually calls apply async under the hood. So down here, when you call apply async, instead of actually doing the work, our overridden OnShift task actually goes and puts it into that list. And then what we've done is we have used the event mechanism in SQL Alchemy to listen for the after commit event. And whenever we get an after commit event, we basically go through everything that is in that list in the queue, and we actually call the apply async. So I've got another function called commit apply async here, which actually calls the original apply async from the task and does the apply async. And then we just have a real simple thing that, hey, if there's a rollback, get rid of everything that's in the queue. And that, so far, this is fairly new code, but so far in all of our testing we've done, it seems to work really well and solve that problem perfectly. So we're hoping that this is going to work, work really well for us in the future because it solves a lot of weird problems on the producing side. Yes?
So you had a global list of commits, but it looks like your task actually flushes that on the first callback. So if one thing gets committed, everything gets flushed. So you forward everything that's in the commit loop, irrespective of whether it actually has been committed.
So we're assuming that so this is, I believe, what you're asking. So the question is when we're committing, why are we clearing out the entire, we only have one queue. So the assumption is that there's only one session, and anything that you can commit is in that one session. So whenever you say session commit, it's committing everything in there. So as soon as you've committed everything in there, you're now flushing everything that you want tasks added, and then it's safe to delete the queue, all the stuff that you're waiting to queue after you've queued it all. So I believe that is safe. If somebody thinks that I might have missed something there, feel free to tell me, because then I can fix a bug before it actually happens in production. Okay, so now the other side of this is so we're using SQL Alchemy now, and we need to figure out how we're going to use that on the worker side. So on the worker side, when you basically want to have one so the idea is I have a task. And like a web request, on the web request side, SQL Alchemy, the way you normally set it up is we create a session, and we attach that session to you attach a session to the web request, you do a bunch of stuff. When the web request is over, you commit the transaction unless there was an error, in which case you roll it back. Well, we want to have the exact same kind of feature here, where we want to commit the transaction if the entire task succeeds. If the task failed, we don't want to commit the transaction. So we are actually able to do the exact same thing, the exact same type of thing here. So this is, once again, this is our overridden task, and there's a few things that we've done here. Now this is kind of weird, and I still keep thinking that this is wrong, but whenever I look at the code samples that are on various Celery things, this is how you're supposed to do it. So you basically, you set up an underscore call, or a dunder call, or whatever you want to call it. And that's where we set up our session, where we basically say, hey, here is our SQL Alchemy session for this particular task. And then we do return self-run, and that actually goes and runs the task itself. And then what we have here is a whole bit, just like we had in the on failures. In fact, here's our on failure again that we saw earlier. Except now, as you can see in this one, now in our on failure, the very first thing we do is we say, hey, if we have this is just some checking to make sure that there's not some weird issue going on. But anyways, if we have a session, then go ahead and roll it back. And same thing, if we have a retry down here, we want to make sure that we roll it back. If we have a successful thing, we want to commit it. And then after we're done with everything with the task, the very last thing we want to do is remove the session. Once again, this is another one of these things with SQL Alchemy. When you want to remove your session, you call session remove instead of your actual instance of a session. It seems kind of weird to me, but it's the way they tell you to do it in the SQL Alchemy documentation, and it seems to work, so I haven't messed with that a whole lot. But if somebody has seen where that's wrong, please let me know, because I would like to know before I get this stuff in production. Because this code is actually not, this code is in our testing environment right now, but we have not moved it to production yet. It'll be a while for this. This is all very new. So, all right, the next thing that we're going to talk about. So, we've talked about, Python code, and we want to create some, we want to create things from Python and create tasks, and we put those tasks in there, and the queue handles them and stuff like that. Sometimes that's not what we want to do. Sometimes we want to say, hey, Postgres is going to create the task itself. For instance, if you want to have a trigger set up that upon changing this particular row in the database, I want to make sure I create a task that Celery wants to do. Now, Postgres doesn't, there's two ways you could do this. The way we chose to do this is we're using a Postgres extension called PGAMQP. To do that, which is basically it is it's C code. That's C code that talks to AMQP, so it talks directly to Rabbit and it puts things into the Rabbit queue. The thing you have to do if you're going to put things into the Rabbit queue for Celery to consume, you need to make sure that you put it in a way that Celery can actually understand it. The first issue we ran into with doing this is the default implementation of PGAMQP doesn't send the content type. If you don't have a content type on something in Celery, Celery just throws it out and ignores it. And we found that out the hard way when we couldn't get anything to work. So basically what I ended up doing, because I didn't want to really get deep and heavy into the C code, is I put a little hack in there that hard-coded the content type to JSON for everything that our particular instance of PGAMQP is sending out. So if you're interested in using that, it is on a public GitHub, and feel free to use it. Someday, maybe, if I have time, my ample amount of free time, I have that, really, I do. Anyway, if at some point, it'd be much better to be able to say set the content type in a config somewhere in the PGAMQP thing. This worked, we got past the problem, and that's kind of what we do it. So the other thing that we kind of ran into, was naming of tasks. So in Celery, your task names are generally set up, if you don't actually give a name for it, it uses the path to your particular task as part of the name of the task. So that way, if you happen to have two things in two different modules with the same name, it doesn't cause a problem. So what we ended up doing is there's an option, and you probably saw it in some of my previous examples, where you can set a task and give it the actual name you want to have. So we just made sure that all our tasks that we wanted Postgres to be able to add to, we just made sure we gave them specific names so that it was very easy to know exactly how to call them from inside of Postgres. And then it's as simple as this is an example from inside some PLPGSQL inside of a trigger function that goes and puts something into a queue that can actually be read. So, the first parameter here, this one here, that is the actual row in the AMQP table that gets created when you do the create extension for AMQP. It's in its own schema of which particular RabbitMQ server you want to connect to, and it has all the connection information and stuff. So that's that one. And then you have to pass it your what queue. Now, it's in here twice because in RabbitMQ you have queues, and then you have the other thing that I can never remember the name of because I'm horrible at remembering names, that is actually the routing information about how you get to the queue. And I've forgotten that. Every time I've given this talk, I've forgotten what the actual name of that thing is. So that's why it's in there twice, because one is the routing thing, one's the actual name of the queue. And by default, they happen to be the same name. And when you set it up in Celery, by default, they're the same name. And then we actually give it the name of the task. As you can see, we're basically handwriting JSON. If you're using a newer version of Postgres, you might be able to use some of the new JSON data types to make this a little cleaner. We're not using that version, so that wasn't even an option for us. But basically, got some kind of handwritten JSON here that says, okay, here's our task name. It's called handle HPPD. Our arguments are a list of the organization ID. Once again, this is a trigger, so this is all just saying, hey, get the organization ID from the original row in the trigger for this particular one. We're converting it to text because this is JSON. JSON needs to all be in text, otherwise you're going to get a syntax error when you try to concatenate all this stuff with those pipe operators. We have another parameter that we just happen to be passing null to. And then the other thing that is interesting down here, some more parameters. The other thing that's interesting here is inside of anything in Celery is expecting an ID for the particular task. So this is where we give it the task ID. By default, Celery just uses UUID to generate a task. So we just kind of did the same thing here. You can, as long as it's unique, you can actually use anything you want. But since like in our case, the IDs from the database could have been reused and stuff, because you could have it in there more than once, that wasn't a valid option to make sure we had uniqueness across there. So we just used the same thing. We just used UUID generate, which is one of the standard extensions that you can just do, create extension UUID inside Postgres, and it'll make it available for you. It's part of the contrib modules for Postgres. So, if anybody has any questions, I'll take questions now. If you want to contact me, my personal email is mike@robillard.com. My Twitter's @mrobillard. And quick plug for the company I work for, OnShift is looking for developers and QA staff. So if you're interested, please send resumes. You can send them to me and I can get them to the right person. That's my work email. So, any questions?
Do you have a single failure queue, or do you have one per message type, or one per exception type, or anything like that?
Okay, the question was, do we have a single failure queue, or one for message type, or one, how do we break that up? At the moment, we have a single failure queue. It's actually a single failure queue for environment, like I mentioned earlier, we have multiple environment thing. But we have a single failure queue at the moment. We have actually discussed breaking that up, because one of the issues that you have in Celery is the queue itself is kind of a black box. It's really hard to go into the queue and see what is in a particular queue without actually pulling the item off the queue and looking at it. So one of the things that we've thought about is possibly dividing that failure queue up so that when we have failures, we can work on classes of failures instead of having to work on the entire failure queue at one time. So that is certainly something to consider. We haven't actually come up with a good solution for that problem yet, and it's definitely a problem that we are trying to figure out a good solution to. Any other questions?
How did you choose to go with Celery in particular?
So why do we choose this? Oh, so the question was, why do we choose to go to Celery in particular? So we knew we were looking for a good queuing system, and we knew we wanted a good queuing system that had good Python support because we're completely a Python shop. So we looked at RabbitMQ, and we didn't really look at ZeroMQ. We looked at the Apache Q one, which I am blanking on the name of right now. And what was it?
Kafka?
Yeah, I think that's it. So we looked at some of those, and what it really came down to was there were lots of good libraries for using, particularly Celery. There were lots of good libraries that had a lot of features that we didn't want to have to build ourselves. And that's why we kind of chose RabbitMQ. And then our choice at that point, once we had chosen RabbitMQ, was basically between Celery and the lower level library that somebody did a talk on last year. I always forget the name. I'm horrible with names. I apologize for that. That's I think it's PyRabbitMQ or something like. No, that's not it. No. Anyways, there is another AMQP. I think it's PyAMQP actually, or something like that. There's another AMQP library that is not related to the Celery project that that people use, but it's much more low level. It doesn't have a lot of the Pico. Yeah, that's it. Thank you. Thanks, Eric. Anyway, that was the big thing. That was the main reason why we chose it. Is it had a lot of features and stuff that we didn't want to have to build ourselves in it, and it supported Python really well. Those are probably the main two reasons why we picked that over any other solution for it. Any other questions? All right. Thank you guys very much for listening to me. So we chose Celery. That's actually will work though. So we chose to use Celery. So what is Celery? Celery is a library for doing queuing in Python. It doesn't actually implement the queue itself. It is just a library for using a back-end queue. Most of the time, people use RabbitMQ as their queuing library when they're using Celery. You can also use Redis. I believe you can actually use Postgres as a back-end. Is one of the options. There's several other backends, but Celery was really built to work with RabbitMQ. It has a lot of specific stuff to make it work well with RabbitMQ. And it uses the AMQP protocol to talk to RabbitMQ. So theoretically, anything else that uses the AMQP protocol can also work with Celery. And one of the other things that's important to know is your workers in Celery. So, when you're doing a queue, you have workers are also called consumers. In Celery, by default, those are an element in that queue. It said, hey, you need to go and move this over to the data warehouse. And we ended up having the worker process, kept reading that queue, and read it. Kind of worked. I mean, it worked okay, but we were getting up into the point where we were doing millions of these. A day. And that began to really cause some problems with Postgres. Postgres has a lot of really good concurrency things. It has row-level locking and all this stuff. But when you start doing millions of things and you're doing, 100 or 1,000 things in a second, you get to these edge cases that concurrency still causes problems, even with things like row-level locking and stuff like that, where everything would be fine except 1 in a million things would be duplicated. And that's not something you want when you're doing queues. You want each thing to be executed once. You don't want something to get executed 2 times. We came up with some workarounds for it, so you can still do this in Postgres. But in order to do that, we basically had to shard the table based on some factor so that one worker could only ever access one section of the data, which doesn't scale real well. It has some scaling issues. Other things that we saw table bloating issues. So we're putting millions of things in there in a day. This table would go from being, having 1,000 items to it to having hundreds of thousands back to 1,000. And the size, according to Postgres, the size of this table was huge when in reality it was small. Vacuuming became a problem for it. So, it just ends up that when you get to really big things, for small things, a queue in Postgres works okay. But when you start to get to doing big things, Postgres is not a queuing mechanism, and it doesn't work well for that. So we were looking for a better alternative. And we decided to choose Celery and RabbitMQ. So I just realized I skipped an entire slide, or it's not on here. I just skipped it. Sorry about that, guys. Okay.
You're ready, go.
All right. Good afternoon, everybody. My name is Michael Robler. We're going to talk about implementing Celery. And let's get started. So basically what we're going to talk about today is implementing Celery. We're going to do a super quick review. There was an excellent talk yesterday on Celery. So hopefully if you don't know what Celery is, you went to that talk. I'll give like a few basic bullet points on it, but watch that talk if you need a lot more details on the basics of Celery. We're also going to talk about what we did at OnShift, the company I work for, before we were using Celery, which will kind of give you a reason why you should use Celery for these type of problems. We're also going to talk about how to handle various problems that you're going to run into when you actually try to implement Celery in a real system. Things like I have multiple environments, I need to handle priorities, I need to handle failures, I need to work with my ORM, and I want to work with the database directly in some cases too. Hopefully we'll get to that one. It's kind of a bonus feature if we get to it. All right, so who am I? I'm the senior architect at OnShift Incorporated. We make scheduling software for healthcare. I'm also the director of technology at EHR Tutor, which is a startup that is making software to help students learn the basic concepts of electronic health records. We're also playing with some really cool polling software, which you guys may have seen in the lightning talks last night. We're trying to get bugs worked out of that. I wrote a computer game called Railroad Empire a while back. It's no longer active. And last year I gave a talk about ORMs here at PyOhio. So I have talked here before. So what did we do before we switched to Celery? So we have an issue in our application where we want to do real-time data gathering and put it into a data warehouse. And in order to do that, originally what we did is we basically implemented a queue inside of Postgres. And every time we made a change to a table in the database, we basically